ECAM FME, Graduate School of Engineering, presents Design and realization of an experimental platform for supervision and monitoring of energy efficiency in smart buildings based on cyber-physical systems. This platform actually represents a part of the project Creative Lab FabLab TRANSENE. The project FabLab TRANSENE is focused on an energy transition via most advanced tools and concepts, including cyber-physical systems. The project is developed by ECAM FME with the financial support of ANRU, National Agency for Urban Renewal, and FEDER, the European Regional Development Fund, and also in collaboration with the Technical University of Sofia in Bulgaria and Logolite Engineering in Sofia, Bulgaria. Our project is in fact a pioneer in this field. The habitat is and will remain one of the major stakes, at least for the next 30 years, both in terms of the comfort needed by the occupants, but also in terms of the energy bill during and after the construction. Significant researches have been carried out in public and industrial laboratories in order to develop new materials, intelligent, economic or others, as well as new methods for construction and management of buildings. These researches are relayed generally by various scientific books and publications, and notably by international conferences increasingly active in these fields, such as ICOM, ECOS, EVF, and others, just to mention a few of those organized in France. This project involves the original use of a cyber-physical system technology, which will be used for agile monitoring and intelligent control of smart buildings. Therefore, an experimental platform for testing and demonstration based on cyber-physical systems had to be developed for the purposes of this project. Let's start with the box. It has 3.75 cubic meters of volume and its size is 2.5 by 1.5 by 1 meter. It is built from Bosch Rexroth aluminium profiles and secure triplex glass. In order to simulate, for example, desert conditions, we have infrared heating elements mounted under the top covers. We use them to raise the temperature as needed. The powerful axial ducted fan is used to simulate strong winds. It is mounted on an adjustable bar, which allows us to make manual corrections to the vertical position and the angle of the airflow. In order to monitor the parameters in the box, we have installed various sensors. We have atmospheric temperature, humidity and pressure. We also monitor the speed and temperature of the wind, using this E+E fluid flow sensor. We haven't had it permanently mounted yet, because we are still determining what a suitable position will be, and also its position depends on the position and angle of the fan. We also measure the humidity and temperature of the sand using these two sensors. The last sensor is a dust transmitter to monitor the fine sand particles in the air. It uses optical refraction to detect the particles passing through it. We have used two different kinds of silica sands to fill the box. The bottom layer is 0.63 mm of average grain diameter size, and the top layer is 0.25 mm of grain size. Both these grain sizes are common for the Arabian and the Sahara deserts. All the sensors and devices are connected in this control panel to a small industrial-grade Honeywell programmable logic controller, which is then connected to a powerful server-grade computer. The components in the panel include a master switch to turn on and off the panel, current fuses, 12 and 24 volt power supply units, the Honeywell ML50 PLC unit with both analog and digital input outputs, a frequency inverter to control the rotation of the fan, and 3 relays for the infrared heating. The control server is running a virtual machine with the Honeywell Experion HS and MATLAB software. The idea behind the virtual machine is, in case anything happens, it is really easy to restore the entire system by just copying the virtual machine drive. It also allows us to experiment with various settings without worrying we will break the setup, since even if we do, we can easily restore it. We are currently gathering experimental data which will be used for the training of the neural network. We are also working on the actual artificial intelligence algorithm. What is forthcoming in the next 2 months is to have an OPC connection between the SCADA and the MATLAB. We also plan to install a mechanized roller blind, which we will be able to control from the SCADA as a result to the control decisions made from the MATLAB neural network. We will also install an IP camera and open the necessary ports on the university network to allow for remote access to the SCADA. Using the IP camera and some remote desktop software, you will be able to connect and remotely operate with the experimental platform. Thank you for your attention.